Hi guys, welcome back to Data Every Day. Today we're looking at a data set of 911 calls in the Montgomery County, Pennsylvania area, and we're going to try to predict the type of call based on a bunch of features. So I have some imports here. We're going to be using NumPy and Pandas to work with the data. We'll also be using regular expressions. And then for pre-processing, we're using the Tokenizer and pad sequences function from keras.preprocessing. These are just going to help us take some text data and turn it into a machine-readable format. And then we'll use the standard scaler and train test split function from sklearn for standard pre-processing. We'll be using TensorFlow to construct our model, and it's going to be a multi-input neural network. And I'll show you what I mean in just a moment. Let's start by loading up the data using pandas.readcsv. We can get the file path over here. I'll show you over here. 911.csv. Let's copy file path, paste it in, and take a look. And right away we notice there's 663,000 rows, and I'm actually just going to work with a subset of the data because I just don't want the notebook to take so long. But then at the end, if we want to, we can always just rerun the notebook using all the data. So while I'm working with it, I'm only going to use 50,000 rows. So let's load that in. That loads up much faster. You can see we have 50,000 rows and 9 columns. So let's get a little info on the dataset. Okay, we notice we have, looks like 2 rows that have some missing values. And additionally, there are 1, 2, 3, 4, 5 object columns. So that's something to keep in mind moving forward. Let us start pre-processing. So what I've been liking doing recently is creating one function that does all our pre-processing, called preprocess inputs, and it just takes in a data frame and it's going to spit out our x and y. And so let's just perform the split first so that we can keep checking the results as we go. So we're going to use the train test split function to split the data into x and y. So it takes in x, y, and a train size. We'll have 70%, and a random state. This is just so we can reproduce the split. This function also shuffles the data, so we'll get the same shuffle each time if we use this random state. Okay, so let me just comment that. Split df into x and y. Alright, and now I should also note, okay, I'm sorry, this is not correct. This will go down here. This will be x train, x test, y train, y test. And we're not really going to use this for a little bit. So I'm just going to keep that, maybe I'll comment it out. And then over here, what I actually meant to do is create y and x. Y will be the column we're trying to predict, and x is everything else. So what we're trying to predict actually hasn't been created yet. It's going to be coming from the title column. So how should I do this? Maybe I will just, I'll start doing a little pre-processing first. So let's take a look at the missing values. Data.isInA.sum. This will give us the number of missing values in each column. And we can see we only have 2 columns with missing values. And it's important to understand what kind of columns these are. So if we look back at the data, we have zip and TWP. And something, based on these, it looks like they may be nominal features. But what gives us an even better sense is by getting a dictionary that maps the column name to the length of unique values in the column. So data subcolumn dot unique, and then take the length. So it's column to number of unique values for every column in data.columns. So this just allows us to get a better sense of what kind of features we're working with. If we have too many values in a column, we wouldn't want to one-hot encode it. But zip code only has 99, TWP has 69, so these are reasonable candidates for one-hot encoding. And the good thing about one-hot encoding is it deals with missing values already. No need to fill them in. It'll just be that the one hot columns will have all zeros if there's a missing value. All right. So let's get back to this. Let's just immediately start by creating the y column. So y is actually we're going to get it from here. We want to predict the type of call. So in the title column, if we take a look at the title column and the unique values in the title column, you can see every value starts with either EMS, traffic, or fire, which are the three types. So what we're going to do is create a new column that just takes that first word, and that will be our label. So in here, we'll say create label column and drop the title column. So let's call it type. Type will be our label column. That's going to take the title column and apply a function to it, lambda function. Takes an x, which will be a given one of these. So this is our x, and we want to take just the first word off of x. So we can use regular expressions to accomplish this. re.search will search for a regular expression in the string here being x, and the regular expression we want to search for here is going to be any word characters. So the colon will terminate it, right? So any word characters from the start of the line as many times as possible until we hit something that isn't a word character, which will always be a colon. So the regular expression to do that would be \w for word characters and a plus for any number one or more times, and we also include the start of line character at the beginning. So it says from the start of the line any number of word characters that occur more than once. More than 0 times. And I think that should do it. Then y is going to be the type column, and we'll make a copy. And x will be everything except the type column. So we're dropping it, axis 1. And we'll make a copy as well. Alright, now we can run this and test it out. So xy equals preprocess inputs, and we'll pass in data. Let's take a look. So x, you can see, well, it still has the title column, but now our y, oh, I actually made a mistake. We've got to make sure to capture the string by typing .group and then passing in 0. Alright, now we should be able to see y, and you can see EMS, fire, and traffic. And we take the unique values of that. We can see there are actually just 3 values, and that's going to be what we're trying to predict. We're trying to predict whether a given call is an EMS call, a fire call, or a traffic call. And even more informative than that is if we get the value counts, will tell us how many of each we have. Okay, so let's actually drop this column. If we kept this column in, it'd be sort of cheating. Because we created the labels directly from the column, we're going to have to drop it now because it has all the information we could possibly need to predict the label. We could actually just have 100% accuracy just by keeping this one column and using it to predict this. So we have to make sure we drop title. So let's do that right here. Oh no, this should be df. Sorry. Okay. df dot equals df dot drop title from axis 1. All right. Let's rerun it because I accidentally wrote data. Okay. So now you see the title. Well, what's going on here? We're supposed to drop it. See, it still has the title column. I'm trying to drop it. Oh, I wrote data again. Sorry. Let's rerun it. Okay, there we go. Title column is gone, and now we are continuing onward. So we have our label set up, and we want to take a look at this thing again. So right away, first thing I notice is that this E column has only one value. That means the E column is actually not contributing any useful information to our data. So let's remove it. There's no point in that. We can do that right up here. say drop e column, since there's only one value. df equals df.drop e from axis 1. Alright, and we can just run these again to see how it affects it. And you can see e is gone. Okay. So I think the next thing might want to do is the timestamp. So timestamp is in our standard datetime format. So we can do something very convenient. Let's say create date features, date and time features. So Pandas has a wonderful function called toDateTime that allows you to take a column, and if it's in a datetime format, it will convert it into a form where we can just easily access the year, month, day, hour, minute, and second values straight from the column. So in here, I'm going to pass in df sub timestamp. So it's going to convert this column into a datetime column, and that'll be our new timestamp. And then we're going to create 6 new columns using each value from the original column. So we'll have df sub year, df sub month, df sub day, df sub hour, df sub minute, and df sub second. Okay. So each one of these is going to be the original timestamp column, timestamp, with a lambda function applied, where x, which will be a given one of these timestamps, datetime objects, and we'll get x dot here will be year, and this is why datetime is so useful. X dot month, x dot day, x dot hour, x dot minute, and x dot second. Okay, and then when we're done, we can drop the original timestamp column from axis 1. Oh, I misspelled. I put an E at the end. Just get rid of those. Okay, now you can see we have year, month, day, hour, minute, second taken directly from our original timestamp information. So that effectively converted it into a nice set of features. So we're done with that. Let's take a look at this again. Okay, so let's see. Why is type showing up in data? I did change it, right? I should rerun this. Okay. So these two are numerical columns, right? So we don't have to worry about those. Description. This is a text column, but I'm sure that this description column contains useful information that we're going to want to hold on to. So we're going to have to hold off and just keep in mind we do want a way to make this usable by the model. Zip code. This is a simple one-hot column. There's 99 different unique values, so we're going to create 99 new columns, and there'll be one-hot columns for each possible zip code. TWP. 69 unique values, so this looks like a perfect candidate for one-hot code encoding as well. Address. This is our last one. Address is far too many to do one-hot encoding. So it looks like we want to sort of apply the same sort of encoding scheme to address and description. They're both sort of free-form text that contains useful information, but isn't necessarily, well, we don't want to encode it in a sparse format. It will just take up way too many columns if we were to encode description or address in one-hot form. So what I'm going to do is create sequences with them, and I'm going to feed the sequences into the model. And by sequence, I mean, let's take each word and map it to a unique integer, and then our inputs will be an array of sequences of word to integer mappings. So that way, our model can embed each integer in a high-dimensional vector space, and well, I'll explain more about that later. But let's just get to it. I want to turn these into sequences, and the same for address. So a description column and address column I want to create sequences out of. So let's do that. Let's actually create a new function here called getSequences. And it's going to take in some text. This will just be a column. So we're going to pass in a column, either the description column or the address column, but it will come in as a Pandas series, and so that's what text is referring to. And we'll also pass in a vocab length. So this is the number of words that we want to use in our vocabulary. And we can just give it a default value. 10,000 works well. I'm probably not going to change this. This value works really well. And then we're going to create a tokenizer. And it's going to be a tokenizer from Keras. And that takes a number of words, which will just be vocab length. And the tokenizer does exactly what we want. It's going to take each word and, well, first it's going to feed it through a bunch of filters. So it's going to take care of all the punctuation. It's going to take care of any like special characters. Just remove them, and then it will lowercase it, and it will split it on white space. So it does most of the processing that we need, but also because we're using a dense encoding on these words, and the model will actually learn where to place the words in vector space, we don't have to do too much special processing on the text, because the model will learn which words are similar to others. So if there are two different spellings of the same word, the model will automatically figure out that those words mean a similar thing. So we're just going to use this tokenizer and not apply any further processing to the text. So we're going to fit the tokenizer, tokenizer.fitOnTexts, and we're going to fit it on text, which is just the column that we're passing in. Then let's get the maximum length of a given sequence. So we can get that from, well, we'll call it max sequence length, numpy.max. So we'll get the max of a list given by the length of text for every text in texts. So this will just take texts and convert each entry to the length of that entry. Then we take the max of the list and we'll get the longest sequence in text. And the reason that's useful, oh, you know what? I should do this after. First, we should convert it to sequences. So let's create sequences. And that's going to be tokenizer.texts to sequences, pass in texts. So this is going to apply the tokenizer's transformations to the data. So once it fits to the text, it's going to assign a unique integer to each word that it comes across in order of frequency. So 1 will be assigned to the most common word, 2 will be assigned to the second most common word, 3 will be assigned to the third most common word, and so on. And it will do that for the top 10,000 most common words. Then this text to sequences will actually apply that transformation to texts. So we're going to store that in sequences, and then I'm going to get the maximum sequence length for sequence, for every sequence in sequences instead of texts. Because if we did texts, it would do it character-wise. The length would be given character-wise instead of word-wise. So this way we're getting the number of words, longest length of a sequence. Okay, and then once we do that, the reason I did that is so that we can pad the sequences with zeros. So we want all the sequences to be of the same length. So if we get the maximum length, we can pad it. We can pad them all, specifying here maximum length. And we'll turn on padding post so that the zeros go at the end. And that will give all of our sequences the same dimension. Return sequences. That will be our function. And now let's use it in our preprocessing function. So we'll do it here. Actually, I'll do it down here. So get sequences for the description and address columns. And let's drop the original columns. So let's declare a vocab length. Sort of redundant, but I just want to pass it in case we want to change it at a later time. And then we'll call it desk sequences for the description sequences, is going to be given by get sequences, passing in here the description column of df, and a vocab length given by vocab length. Remember, that's my two parameters here. And then that will give us the sequences for that column. And we'll do the same thing for the address column. Just change this to ADDR, and this to ADDR, and there we go. Then when we're done, let's drop the original desk and ADDR columns from axis 1. And let's return these guys as well. So we'll return desk sequences and address sequences and y. So these three are going to be our inputs. And this is why I was saying we're going to have a multi-input model. We're going to pass in the normal data frame, x, and the description sequences and the address sequences. And then here's our output, our labels. Okay, so let's see what that looks like. Right here, I'm going to include these new ones. So, shouldn't take too long. Oh, sequence is not defined. This should be sequence. Alright, so let's just change this to sequence. Okay. There we go. Let's load that up. I want to take a look at x, and I also want to take a look at the sequences it produces. So here's x. We no longer have the description or address columns, and you can notice that the last thing we have to do is one-hot encode these two columns. Now description sequences looks like this. If we get the shape, it's 50,000 examples, and each one is 24 words long. Now each word has been encoded with a unique integer, and the integer represents the frequency of the word. The lower the integer, like 2, this is the second most frequent word. We can actually check what it is if we look up here. Wait, actually, let me see. Where is it? So the third word of the third to last example. If we go up here, third word from the third to last example is road. So that makes sense. Road is very common. But you can see it's been padded with zeros so that all the sequences have the same length. And then address sequences should be similar. The shape of this, 50,000 examples, but each sequence is 14 words long. Okay. So let's just one-hot encode these two final columns, and then we'll be ready to start building our model. So let's do that. How about right here is good. One-hot. Let's just do it down here. One-hot encode remaining categorical columns. And that's just going to be zip and TWP. So let's create a one-hot encode function. It's going to take in a data frame, a list of columns, and a list of prefixes. And we can do this, first let's just create a copy of our data frame so we are not modifying in place. And then for every column prefix pair in zip of columns and prefixes, so zip will take two lists, which we're passing in here, and it will pair them up element-wise into tuples so that we can iterate through two at a time. And we're going to create some dummies columns using Pandas.Getdummies, and we're going to generate them from df subcolumn. So for a given column, we're going to create some dummies with a given prefix. Prefix equals prefix. And then we're going to concatenate together using pandas.concat the original df and the new dummies columns side by side. After that, we can just drop the original column from which we created the dummies and return the data frame. So, pandas.getDummies, let me just show you an example of what this does. Let's consider the TWP column. If we want to get the dummies for data sub TWP, or why not do X, and no prefix, that looks like this. Each unique value of TWP now has its own column, and there should be a 1 in a given example for a given value. So here, for the last example, Abington was the TWP value, so here we have a 1 in the Abington column and zeros in all the others. Now, like I said, one-hot encoding deals with null values well, in that if we have a null value, we'll just have all zeros across for a given row. So we can also include a prefix. How about TWP? That will just add TWP to the beginning of every column name so that we know where the one-hot columns are coming from. So let's see. Let's do that now. One-hot encode takes in a data frame, a list of columns, and a list of prefixes. So df equals one-hot encode, passing in df, a list of columns, which is going to be just zip and TWP, and a list of prefixes, which we can just have T and, how about Z and T? Make sense? Okay. Alright, so we're almost done. I'm going to run this, run this, run this. And I believe the last thing we have to do is scale the data. Right now, you can see we have all these new one-hot columns, and everything in our data is in numerical form. So it's ready to just feed into the model. Along with the sequences, they are also numerical, so it's ready to go. Last thing is I'd like to just scale this data so that each column takes on a similar range of values. So for that, I'm going to be using the standard scaler from sklearn, and that will just give each column a mean 0 and variance 1. So let's do that under here after we split. So we just want to scale x, we don't want to scale our labels. So let's create let's say scale x with a standard scaler. Let's create a new scaler, and then let's apply scalar.fitTransform to x. So this will fit the scalar to x and then transform it again, store it back in x, so that each column now has a mean 0 and variance 1. However, this returns a NumPy array, and I just want to keep it as a data frame so we can bring it up and view it nicely. So I'm going to turn it back into a data frame and keep the columns the same. Alright, and then there is actually one last step, which is, let's if we look at y right now, it has these three values. Let's actually encode them as labels, as integers, 0, 1, and 2. So we'll say EMS is 0, traffic is 1, and fire is 2. So right here, we'll say map labels to integers, and we're going to create a label mapping. This will just be a simple dictionary that maps each value to a new integer. So we have EMS, traffic, and fire. EMS is going to 0, traffic is going to 1, and fire is going to 2. And all we have to do is say y equals y.replace label mapping. That'll take care of it for us. You can just pass in the dictionary and then it applies the mapping all on its own. Okay, and I think that's it. if we run this, and then let's also just take a look at our desc sequences and our address sequences. This is looking very good. Just get the shapes of these, it's more useful information. Alright, looking good. This should now be 0, 1, and 2. Okay. So now we can perform the train test split. However, I'm not just going to be splitting x and y. We now also have this desc sequences and address sequences to worry about. So let's include these here. Let's just call it desc train, leave off the sequences. Desc test, address train, address test, and let me just, I'll put a backslash to continue the logical line, and include it on the next line so we can see it more easily. Okay, run that. Now we have 8 different sets of our data, and we can begin modeling. Alright, so now we are done pre-processing. Let us start training the model. Well, we want to build the model first. So I want to specify 3 different inputs. Right, we're using 3 different inputs in this model. This standard tabular input, which is called x. Then this list of sequences from the description column called desc sequences, and this list of sequences from the address column called address sequences. So I'm going to create 3 new inputs called x inputs, desc inputs, and address inputs. And each one is going to be tf.keras.input, and the shape is going to be the shape, the first, let me just explain. Here we'll have x, here we'll have desc train, I should make this x train actually, and here we'll have address train. So dot shape sub 1 means number of columns. So each row is coming in, and it has inputs the length of, here, this is the value, right? So if I do shape sub 1, that's just 14. That's because each row has 14 values coming in. So for the x, each row has, I believe it's 174 values coming in. For the description, each row has 24 values coming in, and for the address, each row has 14 values coming in. Okay, so now with those 3 inputs, I'm going to now work on each input's pipeline separately. So let's do x first. We'll create 2 dense layers for x. We'll have x dense 1 and x dense 2. And they're going to be almost identical. tf.keras.layers.dense. We'll give it 128 activations, a ReLU activation function, and then we're going to pass in, to the top we're passing in x inputs. So this input gets fed right in here, and then x dense 1 gets fed into x dense 2. Alright, and that's it. That's all we have to do for x. Now for desc, let's embed the sequences. So just take a look at it. Desc train, this is our train set. We're going to do something called, we're going to use an embedding layer. So I'll call it desc embedding. That's going to be tf.keras.layers.embedding. And embedding layer is super cool. It allows us to embed each word in its own place in a vector space with dimension of our choosing. So it has an input dimension and an output dimension. The output dimension we choose. I think 64 works well for this model. The input dimension we do not choose, but rather is the number of words in the original vocabulary. So we actually specified that earlier over, where is it? here, 10,000, or right here rather. So that's going to be 10,000. And what this is saying is basically, let's take a vector of length 10,000, which is equivalent to one-hot encoding each one of these integers. Right, because there are 10,000 different integers in here, that was our choice. If we want to encode a single one of these words in a sparse encoding or one-hot vector, each vector for each word would take 10,000 spaces to represent. We'd have 9,999 zeros and a single one wherever the word shows up. But that's very inefficient, and a much better way to do it is to map it to a 64-dimensional vector, which uses less memory and less space, but also the layer has weights that are learned that allow the model to send this word to a special place in 64-dimensional space, and we don't actually know where it's sending it, but it will send it to the most optimal place, assuming that it's converging well, because the model will learn where to send it to optimize the loss function. So that will be called a dense encoding, and it is going to be it's how we're going to embed both the description information and the address information. But one last thing this takes is input length, which is just going to be the length of a given sequence, which is also given by desktrain.shape sub 1. And that's it. Okay, so here we're going to pass in the inputs from our desk inputs, and after that, this will return. It will return a 64-dimensional vector for each word, right? So that will end up as, how many is it? 24 by 64. It will be a 24 by 64 matrix. And since it's two-dimensional, we're just going to flatten it down into one dimension. So flatten, tf.keras.layers.flatten, passing in desk embedding. That will make it a one-dimensional vector of length 24 by 64. We'll get a 1500 element vector out of this. Okay, and we're going to do almost like the exact same thing for the address inputs. So why don't I actually put inputs at the end of here? Okay, so we just have to change these. Address embedding, input dimension is the same because we used the same input dimension earlier. Output dimension can be the same, even though we could change this if we wanted. The input length, this will be different. This will be address train.shape1, and it takes in address inputs and outputs. It gets flattened by address flatten, which takes in address embedding. Okay, so all I did was change the names. So now we took each input and fed it through its own little pipeline, and now we're going to concatenate them together. So we'll call it concat, tf.keras.layers.concatenate, and we're going to concatenate xdense2, so the outputs of each section. Desk flatten and address flatten, and make predictions. So our outputs is tf.keras.layers.dense. This is going to output 3 different values, one for each class. It's going to be the probability that a given row is in one of 3 categories, 0, 1, or 2, or if we look at the mapping, is EMS, traffic, or fire. So each one is going to have a probability estimate, and that's going to require a softmax activation, so that each one of these 3 values takes as a value between 0 and 1. And we'll pass in the results from concat into outputs. Okay, and that's it. Model equals tf.keras.model. We've got to specify the inputs. Inputs here is going to be all 3 of these. So X inputs, desk inputs, address inputs, and the outputs is just going to be this final output right here. Then let's just get a summary of the model. And I want to print out the model in a graphical format using tf.keras.utils.plotModel. Alright, and this is what our model looks like. You can see here all the parameters. The embedding layers have parameters. The original dense layer, yeah, it's interesting it's showing them separately here, but yeah, that's fine. These two are for the X. These two are for each the description and the address. You can see the different input sizes for each one, and then they come down to this final weighted output with 3 values between 0 and 1. And it looks like this. We feed in the X, we feed in the description, we feed in the address. They all go through their own little thing and then come down, get concatenated, and then make our final predictions. Okay, so now let's train. First, let's compile the model. So we're going to use an atom optimizer. For loss, we'll use, no, not binary, sparse categorical cross entropy for multi-class classification. And then metrics, we can just use accuracy. And then let's fit the model and store its results in history. Model.fit. The inputs here are going to be 3 inputs: the xtrain, desc train, and address train. And the output is going to be compared to ytrain. Then we'll give it a validation split, 20%. A batch size, 32. Number of epochs, we'll train for 20 epochs and include a callback function, tf.keras.callbacks.reduce learning rate LR on plateau. So when it notices that the validation loss is no longer improving, it will reduce the learning rate to allow us to converge more easily. Alright, let's run it. And I will resume the video when it's done. Alright, so it is finished. Let's evaluate the model on the test set. And you can see from there it's doing very well. So we actually have to pass in not just xtest, but xtest, desc test, and address test. And then ytest to compare it to. And you can see we have astounding results. 99.95% accuracy. Let's just print that out. Model accuracy. We'll display it to 2 decimal places and format the string. Let's put a %sign and format it with, here, let's store this in results and turn off verbose mode, and then format it with results sub 1 to get the accuracy value, and multiply it by 100 to get a percentage. We can also include the loss. Results sub 0, do not multiply by 100, and don't include %. Oh yeah, here's results. Here's the results. Fantastic. Wait, why is this? Oh, this should be .2, .2. And here we don't need that. Actually, let's show it to 5. All right. Yeah, 99.95% accuracy. So really fantastic results. And I love the model. I love the 3-input model. Well, that will sum up today's video. Thank you so much for watching. I hope you enjoyed. If you did, make sure to subscribe, hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.